Okay, I think we can begin. So uh, let's maybe start by sharing screen. Wait, can you see my screen? Okay, great. I think you can now. Okay, so as usual, I'll request that if you can, then turn on your videos. Not necessarily, but great if you can. Um, right. So last time, if you remember what we did, so we proved, Grigoriev's theorem, which gave us a omega n degree lower bound on, this val function for random kxr, which, we informally think of as saying that even so, maybe it's important to maybe point out how we think of this informally. So we think of the statement as saying that, if sum of squares wanted to realize that, this instance we constructed cannot be satisfied, then in fact it requires degree which is bigger than some c times n for some constant c. So sum of squares requires degree bigger than cn, c constant, to realize that, this m constraint n variable random instance we constructed last time is unsatisfiable. So that's what we proved last time, and that's maybe just an informal way to understand what we proved. And today, what we're going to do is basically, today we are going to basically, enlarge this framework of proving lower bounds to derive lower bounds for many, many different problems. Well, we'll do some in the class and many on the homework. That's how it works, right? So today we will make this into a general framework for lower bounds. And the idea would be to, do what you probably did when you first proved the hardness of 3-sat in one of your TOC classes. So if you remember, you worked very hard to prove the Cook-Levin theorem, which establishes that 3-sat is NP complete. And then, you basically spend maybe, I don't know, a few lectures constructing various gadget reductions from 3-sat into your favorite problems. And you derive hardness of coloring and independent set and, I don't know, many other problems, right? And so what we will do is like do a similar stuff within SOS today. We will derive hardness of many, many problems, including independent set, which would be one of our current running examples today, starting with, this hardness for 3xor and some related problems that we saw from last time. So, we will use basically what we proved the last time as basically the analog of, Cook-Levin theorem, or actually more accurately, it's the analog of PCP theorem, because it's as I'll explain in a bit, it's hardness of approximation, not just, NP completeness that, we end up proving. So, that's our goal today. Okay. So we'll basically, general framework of reductions for lower bounds. But, in order to do this, um, we have to even we have to first of all understand what does it mean to find a sum of squares certificate for problems which are not, of the form of kxor. So far, we've spent many, many classes, and we derived some interesting results by looking at pseudo distributions over the hypercube and problems which basically look like maximize a polynomial over the hypercube, right? But if you look at, some of the problems that we're going to look at today, like maximum independent set and all, these are not problems which can be phrased as, maximizing a polynomial over the hypercube. They involve, some, so they are actually, they can be thought of as optimization of polynomials over some constrained subset of hypercube. Okay, so what we will do is, develop So to in order to even ask these questions and prove interesting results about these problems, we have to understand what it means to write a sum of squares formulation for problems which have non-trivial constraints on them. They're not maximization problems on the hypercube. They involve maximization problems on the hypercube subject to some constraints. And so what we will do is we will spend maybe the first half of the lecture in basically as you might have noticed, um, we basically are building our theory, the pseudo probability theory, in pieces, right? Like whenever we need it, we develop some piece, and we have developed some pieces so far. And we will continue this exploration today by understanding what it means to think about constraint problems, etc. So you could think of it as some first half of the class is like some theory building exercise. We will just build like a general way to address constraints. So building a theory of constrained pseudo distributions and constrained sum of squares proofs. And so we will do that. Then we will see how this general theory is indeed a generalization of what we've studied so far for the hypercube. Then we will come back and reinterpret what we proved the last time for kxor. And then finally we will develop this general framework for reductions and prove a lower bound for maximum independent set. So today's example would be maximum independent set, which we will try to do in full, but at the very least sketch after we have done with all of this theory building exercises. And then you will on the homework you'll see a few more examples of usage of this paradigm, of doing reductions within sum of squares. Okay. And so it's like one very general way to understand when certificates do not exist. So it's actually in some sense, when you are trying to design algorithms, it's very very important to have tools to reason when an algorithm of the form you're hunting for cannot exist. And this particular framework that we develop is like one powerful way to do that. And we'll see one more general framework like this towards the end of the class. We will discuss what is called as pseudo calibration. But today we will focus on this reductions methodology. Good. That's our plan for today. Oh, and I forgot to mention, I wrote it here, but I forgot to mention, we will actually not have a lecture on November the 3rd. It's the election day. And yeah, so, we are scheduled for a lecture according to the usual calendars, but there will be no lecture on that day. Good. So let's do this. Okay. Let's build a theory of constrained pseudo distributions and constrained sum of squares proofs. Okay. So here's the most general setting we will actually focus on. So let's maybe label this. That's our goal. And so let's start by describing what's the general problem we are interested in, and and arguing that what we've been looking for is a special case. So let f1, f2 up to f sub m be polynomials so this notation just denotes the ring of polynomials in indeterminate x over the reals, and x is a n variate, so it's x is actually a collection of n indeterminate, so it's a vector valued indeterminate. And we're looking at like multivariate n variate polynomials in this ring of polynomials over the reals. So even though even though we think about polynomials over the reals, when we think about algorithms, etc., notice that we'll have to work with polynomials with rational coefficients. So even though the field that we operate in is always going to be always going to be reals, the input polynomials we would always think of eventually as given with rational coefficients. Okay, that's basically what we are required to do, because we are trying to eventually work with algorithms that run on our computers. But let's not worry about the algorithmic aspects right now. So you can think of FIs as just some arbitrary real polynomials in n indeterminates, right? So consider the following system of inequalities: f1 bigger than 0, f2 bigger than 0, so on up to fm bigger than equal to 0. Okay. So this is just a system of polynomial inequations or inequalities. And given such a system, we'll be interested in, two kinds of problems. Or actually, okay, let's maybe describe the two kinds of problems. So we're going to be interested in to solve two kinds of problems. So two natural problems, about the system of polynomial inequalities, script A. Okay. What are those two problems? Well, one, you would probably recognize as a generalization of the problem you've already looked at a whole lot. So given some new polynomial g, okay, we want to decide if g is non-negative over a. Okay, what does that mean? So, you can think of a as carving out some subset of r to the n, right? In particular, so let's maybe write these informal comments in yellow. So, you can think of A as a subset of Rn, namely, the set of all x where, each of the Fi's is non-negative. The set of all x such that, Fix is non-negative for all 1 less I less m. Okay. And then, you can ask over all these x's where each of the Fi's is non-negative, is G non-negative? So, this question, so one is equivalent to asking, is gx non-negative for all x such that Fix is non-negative for each of the m different polynomials I had. Okay. So this is the most basic problem, we are interested in. And hopefully, all of you realize that this is actually, a generalization of the kind of problems we've looked at right now, so far in the class, right? Why is that? So consider the set of all. So, let's maybe think of it as an example. So here's an example. Let Fi be the polynomial xi square minus 1. Okay. And now consider the set Fix equal to 0 for all I from 1 through m. Well, so this is not an inequality constraint, even though I wrote inequality. Can somebody unmute themselves and tell me why this is fine? Why this is a set of the form I defined above? First of the many trivial questions I will ask today.
Because you can set s greater than 0 and negative s.
Right, absolutely. So, I can just think of, both inequalities for Fi to be added simultaneously. And that's basically, equivalent to forcing that Fix be equal to 0. So the equality constraint. And so look at this, look at the system. What is this system? What set does it define?
The hypercube.
Exactly. It defines, the Boolean hypercube plus minus 1 to the n. And, that's a set that we have focused a lot of our energies on. For basically half the lectures, we've, continuously, hammered on various aspects of, this particular set. So, this is familiar to you. And now, if you look at for this particular set of, a system of polynomial equalities or inequality constraints, then the question of deciding whether a g is non-negative is the kind of question we have basically focused on so far, deciding if there is a sum of squares certificate, or deciding if g can be proven non-negative over the hypercube, right? So hopefully you understand that this question one is basically a generalization of the kind of problems that we have studied so far. Okay, very good. But we will actually study a um, a formally harder problem than this. Okay, we will actually also look at this extension of this kind of problem in that we just defined in one. And here is that question. Okay, decide. So in problem number one, You were given, in addition to system A new polynomial G and were asked to decide if G is non-negative, for all X that satisfy script A. In problem number 2, you are given no additional polynomial. Your goal is simply to decide if A is empty. Okay? That is, decide if there exists an X such that Fix, is equal to 0, I from 1 through M. So, as I already promised, I have only asked you one of the many trivial questions I'm going to ask you. Here is my second trivial question for today. Why is 2 more general than 1? Again, feel free to unmute yourself. And Tim, you cannot answer this time. Somebody else, please unmute yourself and tell me why is 2
We
more
can
general.
add the function minus g to the set.
Exactly. Praneeth is absolutely right. I hope that I got that right. This is Praneeth, right?
Yeah.
Okay. Praneeth, you're absolutely right. So what Praneeth is suggesting is, just look at the problem number 1 and, consider the following system. Fi bigger than 0 and G less than 0. Okay. And now, simply ask if given a set like this, is it empty? Right? So, this is checking if there is some X such that, Fix is always non-negative, while, for there is some X such that Gx actually happens to be negative. Okay. So if this is empty, then you know that, you have a positive solution to the question in 1. If this, on the other hand, turns out to have a solution, then, you have refuted or negatively answered the question in 1. So 2 is actually, more general than 1. And actually, there is 2 is strictly more powerful than 1. And before the class, I spent like 30 minutes trying to think of like one simple example, but all examples I had were complicated. So my homework is to construct a homework exercise for you, which is simple enough and to appreciate the difference between 1 and 2. And so, that I will do by the time, your next homework is out. So you'll discover why 2 is actually strictly more powerful formulation than 1. Okay. Good. Very good. So those are the 2 problems, we are going to be interested in. And we already discovered that 2 is more general. So now, I want to basically extend the kind of concepts we developed for the special case of hypercube to this more general setting. Okay. And think of it as like, some attempt to, build a theory of how to answer both these questions with, the sum of squares algorithm. Okay. So first we will extend our notion of sum of squares proofs. Okay. So we will say, so here's a definition. We will say that, oops. Okay, good. So we will say that there is a, so this is a phrase. So let me define it like this. There is a degree D, or okay, let's call it degree L sum of squares proof that A implies G bigger than or equal to 0 if there exist SoS polynomials P sub S for S subset M, okay, such that G can be written as P sub S product in the multiset S of polynomials Fi. So S, so let's maybe point out, this is a multiset. So you can use, same index multiple times. And, I'm going to call that G has a degree L proof. So I've already given you a form now. Well, I'll say that G has a degree L proof, whenever So, okay, if there is this SOS polynomials and every summand PS product SFI has degree at most L. Okay. So we'll examine this definition, a little bit more in a second. But let me, this phrase is going to be a mouthful. So we are going to define a compact notation, and this is a notation that you'll see in many papers. And so this is your opportunity to learn this notation once and for all. It's very simple. So we are going to denote the fact that there is a degree L sum of squares proof of non-negativity of G over the set A by writing in notation. So notation A okay, so we read this as A derives G bigger than 0 in degree L. That's how we read this. Okay, so you can think of this as the symbol that says derives. Okay, and so we write, so let's maybe understand the mechanics of this notation. So this is the degree of the proof. So on the top goes the degree of the proof. On the bottom goes the variable of the proof. Now, in our setting, because we are looking at polynomials in, just one set of indeterminates, there is no, there is, in the setting we are developing right now, there is no possibility of confusing what is the variable of the proof. So we don't usually have to write down X. But, in the next lecture, we might actually encounter examples where, there are, various kinds of variables, in the polynomial system that you're working with, but you're looking at sum of squares proofs only in one of them. So the rest of them can be thought of as constants. In such settings, you want to clearly identify what is the variable of your sum of squares proof. And when we need to do that, we will just write, the variable of the proof at the bottom in this notation. Okay, so usually we'll suppress it, but if we want to clarify what the variable of the proof is, we write it, at the bottom of this notation. Very good. And yeah, as I said, we suppress when clear from context. Actually, there are opportunities, there are situations where we even suppress the degree of the proof because, for whatever reason, it's clear from the context. And so, we might even end up suppressing this and just like write the derived symbol without, anything written on the top or the bottom. But usually we try to be faithful to, representing the degree of the proof at the very least. Good. So now that we have, designed a notation and defined a concept, let's make sure that we understand, that this concept does what we would like it to do. Okay. So the language somehow, as you've seen in the class earlier, and the language here, this particular representation of G is supposed to be like an immediately verifiable proof for us that G is non-negative over the set A, right? So let's try to understand why does such a representation even imply that? And the reason is very simple, right? Remember that for every X that satisfies the inequality system, right? The FIs here would be non-negative. So the product of FIs would be non-negative, right? PS are sum of squares polynomials, so they are always non-negative. And therefore, what you're constructing is basically a sum of some bunch of summands, which over the set of X's that you care about are always non-negative. And so, such a representation immediately implies that G has to be non-negative, over the set you care about. Good? Make sense? So if such a representation exists, and if I can convince you that such a representation in fact holds true for the polynomial you care about, then certainly you've established that G is non-negative over this set. Of course, when such a proof exists and can such a proof exist, etc., are, issues that we'll figure out soon. But at least if it exists, then you're convinced that in fact it establishes what you wanted to. It solves problem 1. Good? Again, feel free to, stop me and ask questions. We're going to use this technology that we developed today for essentially every one of the remaining 5 lectures. So, we better be clear with everything that we do today. Good. Um, all right. So maybe one thing to clarify, and give you some space to ask questions while I basically repeat things, is to note what it means. What is this an equality of, right? Like, this is an equality of the left and right hand sides seen as polynomials over the reals. Okay, and so these two polynomials are equal if the coefficient of every monomial on the left and right is equal. Okay, so let's maybe point that out. That's what the equality means. So coefficients on left and right hand sides are corresponding coefficients are equal. And that's equivalent to these polynomials being equal as functions over the reals, by, well, by, let's say, Schwarzschild lemma or whatever. By like some basic algebraic stuff, you know that, uh, two polynomials, two multivariate polynomials over the reals are, equal if and only if, all their coefficients are equal. And so, so I'm just pointing out that this equality, you can think of it in both senses, but what is relevant to us and what we use more often is that they're, equal coefficient wise. Okay. Now, just to test our understanding, let's ask the following question. You all recall the definition of sum of squares proofs over the hypercube that we defined earlier, right? Let's try to make sure that this is indeed a generalization, that I somehow, didn't do a bait and switch on you. So remember what a sum of squares proof over the hypercubes were? So there we said um, G has a sum of squares proof of degree D over the hypercube or degree L over the hypercube if G can be written as some Fi square for degree at most L by 2 polynomials Fi, right? And what was this equality? What was the definition of this equality? This equality only needed to be held on the hypercube. We didn't force them to be equal as polynomials over the reals, if you recall. We only force them to be equal as functions on the hypercube. Then we said, well, that is equivalent to G and Fi square, some Fi square, having the same coefficients after multilinear reduction. So why is this equivalent? We just defined SOS proofs in general as this kind of a representation, okay, where the equality has to hold as real polynomials. But over the hypercube, we gave like this special definition where the two polynomials had to be equal as functions on the hypercube, which only implied that they should be equal in the sense of coefficients after multilinear reduction. So why are these two equal? So this is, an exercise in formally checking things correctly. So I will do this, okay? Just so that it's absolutely clear that the definition we just gave is a generalization. So why is this the same? So our semi-algebraic set here. Oh, I should have I should have pointed out to some terminology here. Such sets, intersections of solution sets of polynomial inequalities, are called as semi-algebraic sets in algebraic geometry, which we'll borrow from them. Just a compact notation, compact language for describing the systems of polynomial equations in general. We're just going to call them semi-algebraic sets. Very good. So the semi-algebraic set that we consider in the context of hypercube is simply these equality constraints, right? That's what we thought about so far in the class. And so what kind of SOS proofs would that imply? By the definition that we just made? Well, that would mean that G should be representable as sum over S in N, P sub S, product I in S, right? So far so good. And in the definition we just made, PS were supposed to be SOS polynomials, but here I claim that PS could be arbitrary polynomials. Can somebody point to me again why I can think of PS as arbitrary polynomials?
Because this will be 0 over the hypercube, the product.
Yes, that's one way to think about it. But we defined SOS proofs only for inequality constraints. And so one other way to think about it in the context of the definition we just made is that every polynomial can be written as difference of two SOS polynomials. Every polynomial can be written as difference of two SOS polynomials, and you have when you think of the equality constraints, they correspond to two opposite signed inequality constraints, and so you can just combine the coefficients for the negation of xi square minus 1 that also appears in your system, and and that gives you an arbitrary polynomial. But basically maybe it's like simpler to just define this separately as Mitali suggested, so that there is no confusion. So um, let's okay, I guess I developed the whole thing for inequalities. Okay, let's maybe just add them here. Okay, let's call them h1, h2, and hm prime equals 0. So now I have equality constraints, and okay, so and here these can be arbitrary polynomials. The earlier definition we made is enough, but this is just for the sake of clarity, so that absolutely things are absolutely clear. Very good. So that's what a SOS proof looks like if we use the current definition. Now, why is it the same as the definition we made earlier? So let me let me observe a simple fact. I'll try to sketch a proof of it to you, but not spend too much time. So if G and H are equal as polynomials over the hypercube, then G equals H plus some P S subset N 1 minus xi square product I in S. And let's say H is degree L, then this also has degree at most L over the reals. So two polynomials are equal as functions over the hypercube if and only if G equals H plus something which is basically sum of multiples of 1 minus xi squared, the constraints that appear in your system over the reals. So like the polynomial equality over the hypercube can basically be converted into polynomial equality over the reals by just factoring out, or like having a multiple of the constraints that define your set appear in addition. Okay, and this the proof is very simple. Okay, the multilinear reduction that you do naturally yields such a representation. Okay, so what's the proof of this? So I'm only going to sketch. So let's say for example you try to do it for xi cubed. Okay, now over the hypercube, xi cubed equals xi, right? And I can write it as xi cubed equals xi minus xi plus xi cubed equals xi plus xi square Hopefully I got that right. I think I did. And so, I've written xi cubed as, xi plus something which is a multiple of xi square minus 1. And you can keep doing this trick to, monomials of larger degree in general. And then you can keep doing this trick to arbitrary polynomials. And so, basically the concept of proofs that we studied in the context of hypercube is simply, a special case of, general SOS proofs that we just defined. Okay. Even though, in the general case, we think of representations of the target polynomial, over the reals. So we always think of polynomial equality over the reals now. In the context of hypercube, we thought of, equality as functions over the hypercube, but they're equivalent. Good. Very good. So hopefully, the definition is clear. Can repeat. So let's call it a sketch. Good. So, the natural question to worry is, when do such proofs exist? Or if they exist at all, why should sum of squares proofs exist? We kind of convince ourselves that if they do exist, then they do constitute a proof of non-negativity of G over the semi-algebraic set that we're given. But why should such proofs exist in the first place, right? So here is so remember over the hypercube, we at least had some statement that, there are always sum of squares proofs, of high enough degree, like degree 2n or something. The analogous statement that there are proofs if you allow large enough degree is kind of non-trivial and doesn't actually always hold. Okay. So, and in fact, these are extremely non-trivial theorems that were proven. So I think I'm going to state a version due to Krivine and Stengel, who kind of proved similar results independently. There was a time when you could prove independent results and not know the results for 10 years. Thankfully, today is not that time. Good. So A is that semi-algebraic set that we were given. Then what Krivine and Stengel proved is that then either there's a solution. So I'll point out in a second, but this, you should think of it as a existence of large degree proofs for the second formulation. Okay. We talked about two problems. The second problem was checking feasibility of a system of polynomial equations. The first problem was, checking non-negativity over a system. This version is formulated for the second problem, which we saw was more general. Okay. And it's actually kind of important. I can't quite formulate it for the first problem. I can only formulate it for the second problem. So then either there is a solution to A, that is A is actually non-empty, or there exists a SOS proof that A derives in degree L the bogus equation -1 bigger than or equal to 0 for some integer L. Okay. So this can be somewhat flummoxing. So let's make sure that we understand what this means. So what is this saying? It's saying that either a system of polynomial inequalities that we are given is empty, is non-empty, as in there is truly an x that satisfies all those inequality constraints, or there is a sum of squares proof, okay, of the polynomial inequality, the bogus polynomial inequality -1 bigger than or equal to 0 over the set A. So let's understand what this means. If A derives in some degree L the inequality -1 bigger than or equal to 0, what does it mean? It's a trivial question, one of the many trivial questions I'm going to ask. So again, unmute yourself and answer it away.
The system is infeasible.
Exactly. That's exactly what it has to mean, right? Like -1 bigger than or equal to 0 is a quintessential contradiction. So, in some sense, this is just a fancy way of writing A derives a contradiction. If you were doing, formal logic, this is saying that A derives, false. if any system derives false, it must mean that it is infeasible, it's inconsistent. What is this? So let's try to make sure that we understand, in terms of polynomials. Okay, what does this mean? One way to interpret this derivation is that if there was an x that satisfied all the inequality constraints that appear in the system script A, then it would imply that the polynomial -1 is bigger than or equal to 0. And because there cannot be such that, like this latter conclusion is clearly false, there cannot be such an x. So in some sense, the condition here is saying that it is some certificate that A is indeed infeasible or empty. Okay, makes sense. So I want to point out, you could have imagined a version of this theorem that says that if G is non-negative over a semi-algebraic set A, then there is some large enough degree sum of squares proof that G, is non-negative, that there is a large enough sum of squares certificate for G. That's not the one I stated here. Okay, and there's a good reason for it. In general, that's not true. Okay, so even though of course in some sense it doesn't lose us anything, because we can simply throw G, like G is negative, as an additional constraint, like we did, and then just check for whether there is a bogus derivation, like A derives -1 bigger than or equal to 0. So because this is a very special kind of derivation, by the way, we're going to call it a special name. We're going to call it a refutation. So we're going to think of this particular statement as saying that, I have refuted the system A. I have found out a proof that they are infeasible. Okay, very good. So hopefully, again, I should point out names. So such theorems are called by the fancy German name positive Stellensatz. One reason I was, I guess, not pointing it out is because I don't think I can ever pronounce it right. But I know that my mathematician friends, do this trick where they actually don't pronounce it in full. They pretend as if they're like shortening it. They call it null sarts and positive sarts, and they pretend as if it's just like a shortening. But I really know that it's because it's so hard to pronounce. That's the reason here. Anywho, good. So we understand, the statement. That's good. It tells us that, at least in a certain sense, there is always a refutation if you allow large enough degree. But of course, this theorem is, the proof of this theorem is highly non-constructive. And in general, produces no bounds on the degree L. So even though, it just proves that there is an L for which, there is refutation like this, and generally doesn't give any bounds on L, when we are working with, a certain system that we care about for like an optimization problem, then we are usually interested in, fixed bounds on L. And so in general, we have to work quite hard to, prove non-trivial bounds on L, which is not a surprise. You have to work for any interesting result. You can't hope to, coast on the shoulders of Krivine and Stengel. But just so that I pointed out, very good. So one nice thing is that and in fact it's very important if we had like in the analysis of our algorithms and proof of our lower bounds, we have to work with various kinds of sum of squares proofs. We've kind of been working with them so far already, and I'll point out how we've been doing that today, because now we have developed this new terminology. It would become horrendous to work with these proofs if there was no simple calculus for them. By that I mean that if there was no simple way to combine existing SOS proofs, then it would become very, very hard to prove every new inequality and like derive new SOS proofs for a given polynomial, because you basically will have to start from scratch and like discover these weird representations. But the cool thing is that you don't have to do that. You can actually start with some basic things and build new proofs from them. Okay, and so what we will do now is describe the simple calculus for proofs, how to combine SOS proofs and produce new ones. Okay, and I'm going to call them rules, but basically they are really theorem statements. They're saying, so let me maybe state one before I pontificate on it. So the addition rule states the following: says that suppose a system A. So in the system A, B, and C would be just systems of polynomial inequalities. So suppose we have a degree L sum of squares proof that A derives F bigger than or equal to 0 and also G bigger than or equal to 0. Here is how we'll write that, okay? And notice I've suppressed the variable of the proof because, it's some fixed X, okay? Then, so, I'm the, so, on above this horizontal line, I write things which are my hypothesis, and below I write conclusions. So then A derives in the same degree L, F plus G bigger than or equal to 0. Okay. So this statement says that, if A derives in degree L, F bigger than 0 and G bigger than 0, then in fact, it derives also in degree L that the polynomial F plus G is bigger than or equal to 0. Okay. And I'm going to call this the addition rule. And as I said, even though I call it a rule, it's not like a law of nature, it's a theorem. So time to unmute yourself and tell me a proof of the addition rule. I promise I'll ask you only for this one and then write the other rules and keep quiet. Okay. I'll not ask you again and again. Just this one, I do want you to tell me.
Just add them, the coefficients up to
Exactly. Yeah, Misha is absolutely right. If F has a SOS representation, this particular representation that we wrote down, and G has a particular SOS representation, then addition of it actually gives a new representation for F plus G, and that constitutes a SOS proof for F plus G. It's very, very simple. Okay, so these are not hard theorems. That's why I'm calling them rules, and that's why I'm not proving them. But these are extremely useful, even though they are simple observations. So that's the addition rule. There's a analogous multiplication rule. Just says that if A derives in degree L FG, and by FG now I mean F bigger than or equal to 0, G bigger than or equal to 0. You see, I'm already getting tired of writing this repeatedly. Then A also derives in degree L. Wait. I hope I got that right. FG bigger than or equal to 0. Make sure that I got this right. I feel like it might be a bit larger.
With 2L.
Yeah, I think it should be 2L. You are right. So actually, okay, maybe the way to write it seems like I do have to write it like this. Then there's an L plus L prime degree proof that FG is bigger than or equal to 0. Okay, and I hope you see the proof for this too. But this time you're just going to take product of the representations, and note that degrees of polynomials add when you multiply them. So that's why L plus L prime. Good. So you now know the multiplication rule. Let's write the transitivity rule. It says the following. Suppose there is a degree L proof that A derives a bunch of polynomial inequalities that appear in system B. So now, this statement is saying that, for every polynomial inequality that appears in the system B, there is a degree L proof starting with A. Okay. And let's say that B derives in degree L prime some other system of polynomial inequalities C. Okay. Then I can string together the proofs and note that A derives in L times L prime degree system C. Okay, and again, this is obtained by just unfolding the proof. So there is a proof, of degree L prime for every polynomial inequality that appears in C in terms of the system B, and then you take every SOS every polynomial that appears in system B and replace them by the SOS proof that comes from A. If you unfold this proof together, you will get a degree bound of L times L prime. And so, this tells you that, you can, so this is an extremely important rule, because what does it tell you? It tells you that, if you start from like a bunch of polynomial inequalities that appear in your system A, derive a set of new inequalities, and then just treat the new inequalities as your new system and derive further new inequalities, it's fine because you can string them together. You can get like a proof from the original system. Okay. And so this transitivity rule is very important because you can build new proofs by just like adding to your system repeatedly. Good. That's the transitivity rule. And the last one I want to point out is the substitution rule. So let's say f, is a collection of m polynomials, or actually, let's say, yeah, f is a collection of m polynomials. See, okay, and let's say G is a collection of. Okay, I guess I didn't write down the notation for that. I'll figure out when I write it. Let's say, H is a collection. Let's maybe write G is a collection of P polynomials. And H is a map from Rn to Rp. Then if the system F bigger than or equal to 0, this means that, every constituent every one of the constituent M polynomials of F is bigger than or equal to 0. Suppose it derives in degree L, that every constituent polynomial in G is bigger than or equal to 0. Then I'm so, F, let's say, is in variables x1 through xn. Okay. I'm going to replace each of, the n variables, okay, by, polynomials, by like this H gives me a map from, the variables into, some new variables. Okay. So H is giving me a substitution map. Okay. So H tells me, replace x1 by some other polynomial. Then this rule says that f of h bigger than or equal to 0 derives L in degree L times degree of h, g of h bigger than or equal to 0. So hopefully I got these numbers correct, but the point I'm making is here is that I can substitute polynomials for variables, and so if f bigger than or equal to 0 derives g bigger than or equal to 0 in some variables x, and I substitute each xi by a new polynomial, then I get I get like an analogous derivation in the new substituted variables. Okay, good. So these well, I guess you could build more rules, but these 4 are more or less enough to do a whole lot. And so we will you'll see that we are going to use them repeatedly in the classes to come ahead. Good. So we know how to combine basic SOS proofs now. Let's go to the next part. Define pseudo distributions more generally. Okay, so now now is the time to generalize the definition of pseudo distributions that we did on the hypercube. So remember what we did there. So mu was just a so over the hypercube, mu was just a function from plus minus 1 to the n to r, and then we post some conditions on it, right? Now actually we have to define pseudo distributions in general over Rn, because our polynomial systems are not over the hypercube anymore, right? So the functions we will consider now, the pseudo distribution defining functions, would go from Rn to R. And in order to avoid all measurability and convergence issues that come with dealing with continuous functions, right, or like functions on continuous domains, I'm going to force that this is a function which is always finitely supported. So what that means is that mu is non-zero on all but a finite set of points. Okay. Good. Oh, sorry, did I say that right? Mu is 0 on all but a finite set of points. Good. Good. So given such a finitely supported function on Rn, I define the formal expectation just like we did in the context of hypercube, but this time, I can write it as a summation because mu is finitely supported. So there is no integration happening here. Mu x dot fx, no surprises there. This is the formal expectation, the analog of what we defined on the hypercube. And it works because, we're just saying that, there's going to be a summation over some finite set. Good. So now I get to define pseudo expectations or pseudo distributions. So let's point out that this is a definition of pseudo distribution. So a finitely supported function mu from Rn to R is a degree D pseudo distribution if And this time, I don't kid around. I just simply write down the conditions in terms of, the pseudo expectations. So if you remember, these are direct analogs of, in fact, just exactly the same conditions that we wrote down on the hypercube. For all f of degree at most d over 2. Okay. And, just to carry over the language that we were using in the context of the hypercube, we'll say that if support of mu is a subset of some set omega, subset of r to the n, then we know we're going to call mu, we'll also use the terminology that mu is a degree d pseudo distribution over omega. That's what we will say. Okay, so that's, as you can see, we literally just lifted the definition that we had for the hypercube and like just extended it to these more general domains. Good. And just like in the context of the hypercube, there is a natural connection, an important connection between pseudo distributions and positive semi-definite matrices. That's the reason that we can do things with them. That's the reason that we can find them using algorithms. So here is the analogous connection for these more general pseudo distributions. So say mu, finitely supported function. And let's say, that this is always 1. So remember, this just means that, sum over x, mu x not 0, mu x is 1. That's what it means. So suppose mu is some finitely supported function such that the formal expectation with respect to mu of the function 1 is 1. Then mu is a degree d pseudo distribution if and only if the matrix is PSD. And the proof of this is exactly the same as in the context of the hypercube. There is literally no change that happens. You can go back and check the proof if you've forgotten, but it's the same proof, so I'm not going to do it. I am going to point out though that this matrix here has a very nice name that we'll keep using. We probably are already using it. We'll call this the pseudo moment matrix. Okay. And what we are saying is that, mu is a degree d pseudo distribution if and only if the pseudo moment matrix is positive semi-definite. Good. So that's very good. And that's actually not even that surprising because it's literally the same thing. The new thing we did today is like define what, how to deal with constraints, right? And so what I now want to do is like extend the definition or like give you a definition of what it means for a pseudo distribution to satisfy constraints. Okay. I'll pause after that. I know there is a lot of theory building going on, so maybe I'm boring some of you, but it's like, I don't know. It's a little bit like cereal, right? You've got to have breakfast to do good work till noon. And the breakfast can be boring. It could be a bad cereal, but we've got to do what we got to do. I promise I'll take a break I'll take a pause after this, and we'll discuss some cool things. But let me make this new definition because that's where at least some new stuff happens. And so this is the idea of pseudo distributions satisfying some constraints. So again, same setting, mu is Rn to R, finitely supported. Let's say it is pseudo distribution of degree D. And let's say A is a system of polynomial inequality constraints. Then we say that mu satisfies system A. Now, this can be somewhat confusing, so I'll explain why I'm doing this in a second. But I'll say that mu is a degree D pseudo distribution, okay? But I'm introducing this extra parameter here. So mu satisfied satisfies the system A at degree L if for all S subset of M is the number of inequality constraints in the system A, and every SoS polynomial P I guess let's call it H, such that degree of H plus some I in S degree Fi. Okay, sorry. Okay, so let's let's forget about this part for a second, and try to appreciate what's going on without that. Okay, so let's forget the degree constraints here. Okay, I want to talk about what it means for a pseudo distribution to satisfy constraints. Okay, actually, maybe what might be easier is to maybe as an example, let's maybe to appreciate this definition, let's for an example consider equality constraints. Okay, so what does it mean for a pseudo distribution to satisfy? So mu satisfies the constraint, let's say f equals to 0, just a single constraint, if for all polynomials h e twiddle mu h times f equals 0 whenever degree of h plus degree of f is at most d. This seems, so let's say mu of degree d satisfies f equals 0 at degree L, sorry, at degree also, let's say wait, at degree d minus degree f, I guess. Okay, so let's again table the question of what this degree, oh no, let's table the question of what these degree bounds are for a second. Okay, so let's ignore this and consider this condition, because that's first of all easy to appreciate. We are saying, so we are trying to we are in some sense we are trying to import some properties that actual distributions that are supported on solution sets of polynomial equality constraints must possess. Okay, and then we are like trying to lift them and like derive consequences that should be true for pseudo distributions. So notice that if mu was a distribution supported on solution set of the polynomial equality constraint f equals 0, right? If mu was supported on any x or on the set of x's that satisfy f equals 0, then it would definitely hold that expectation of mu of any function h times f must be 0. Why? Well, because mu support, for every point in mu support, fx equals 0. So h times fx equals 0, and therefore the expectation of hf must be 0. Right? So far, so good? Good. So so this would have been something that is true for all functions h for an actual distribution mu. We are deriving a consequence. We are deriving a consequence that holds for low degree polynomials, and we are forcing it in our definition of satisfying a constraint for a pseudo distribution. Okay. Similarly, if I had a constraint f bigger than or equal to 0, okay. So what would it mean if mu, a distribution, was supported on solution sets to this system of solution set to this polynomial inequality constraint? What would it mean? We mean that if I take any h which is non-negative, so if h is a non-negative function, then it would hold that h times f has non-negative expectation. Why would it hold? Well, because for every point x in the support of mu, fx has to be non-negative. H is a non-negative function, so h times f always has to be non-negative, and over the support of mu, that's where the expectation must be non-negative, right? So these two are facts that must hold, for actual distributions. Now, what we did is, did what in some sense we did our best to import, them faithfully into the world of pseudo distributions. That's what we did. Okay, so we can't quite reason about non-negativity. We can only reason about sum of squaresness. So we replace this condition of h being non-negative by h being sum of squares. So you see here, for example, that the condition we wrote down has only SoS polynomials h appearing. And this product of FIs are what are rendered non-negative, by the system A. So we are trying to, enforce the condition that the pseudo distribution be supported on solution sets to the system of inequality constraints. We're saying, okay, if this was a true distribution, what would have held true would be that, if I take any product of FIs that's non-negative, if I multiply it by a non-negative function, it gives me a non-negative function of the support, and therefore it must have a non-negative expectation. And I just derived a consequence of it that in some sense seems reasonable for pseudo distributions to possess. And that's basically what's going on here. Now, what about this degree business? Like, why am I forcing this weird condition? So first of all, let's try to understand what's the natural degree constraint to enforce. Now, if mu is of degree d, then I can only compute pseudo expectations of degree d polynomials. So the natural constraint on degree should have been that degree of h plus sum over I in S of degree of Fi is at most d, right? That would have been natural. That's just saying that, this polynomial is of degree at most d. What I did is like slight modification. I'm actually paying more than degree Fi. I'm paying, so if degree Fi equals L, then there is basically no contest. But if degree Fi is strictly smaller than L, then I'm saying that, okay, you know what? I'm still going to count the degree of this polynomial as L. Okay. So the reason I'm doing it is because, I want to separate the extent to which mu is a pseudo distribution. So mu, gives non-negative values to all degree d over 2 polynomials. So this d in some sense denotes how much of a pseudo distribution mu is. I want to separate it from, to what extent it satisfies the constraints. And so, this L is a knob that allows me, like in some sense, if L is large, then, it satisfies the extent to which it satisfies constraints is lower than what it would have been if I just enforce it for, all degree D polynomials like this. Like, the true degree of this polynomial now is going to be small, right? Like imagine that FIs are of like degree 1 or something, right? And let's say L is 2, right? Then the constraint that I'm enforcing are on much smaller degree polynomials than D. Okay, I'm ignoring, oh no, oops. So, if I didn't have this, if I didn't have, this max over here and I just had degree Fi, then I would have enforced this constraint for all products of H and Fi, so long as, the degree of the product is at most D. Because of this max here, I'm actually forcing it at a slightly lower degree. And this is just to allow myself, some technical freedom in separating to what extent mu is a pseudo distribution and to what extent it satisfies constraints. And this would be nice when I write down, some ways to combine SOS proofs later on. Otherwise, this won't be necessary. This is just a technical trick I'm doing so that I can write down a meaningful statement and how to combine pseudo distributions later on. So you can even like ignore this distinction between max degree Fi and L for now. Like just think of it as degree Fi here. And then this is just saying that, whatever constraints can be derived in degree D, I'm going to force that. Okay. Let me take a pause for 30 seconds and see if there are any questions or confusions that I can answer.
If G has a sum of squares proof of degree D in this system over FIs, then this
Okay.
max, then the pseudo expectation might not be as in confusing. Like,
Yes, absolutely. So, right. So, okay, so this is a good point, and maybe I'll write this down. So what does it mean? So corollary. If G has a degree L SOS proof, oh, I developed notation and then did not use it. So let's do that. If A derives G bigger than or equal to 0 in degree L, then and mu, okay. Two things. Sorry. I forgot to give you notation for this, compare something that we just defined. So I defined what it means for mu to satisfy constraints at degree L. I'm going to write this in notation as mu so this notation comes from formal logic, and actually it means mu is a model of. Okay. You can call it that, you can call it whatever else, but the terminology here is borrowed from like formal logic, because we are trying to understand certain simple kind of proof system. So this is basically some proof system lingo going on here. And so this double thingy, like the double version of derived symbol that we wrote earlier, just means is a model of. So in some sense, if you know a little bit of formal logic, then pseudo distributions are models, in a formal sense, of the system of axioms A. But ignore this statement if it doesn't make sense to you. Formal logic is not my goal. Good, but I'm going to write, so we are going to just simply read it as, so the formally the symbol means is a model of, but we are going to just read it as mu satisfies A at degree L. Okay, so we're going to ignore all details of logic, just going to call it mu satisfies A at degree L. And so now imagine that A derives G bigger than or equal to 0 in degree L, and mu satisfies A at degree L, then so this actually has a simple proof, and it's like an exercise in opening of definitions. So A derives what does A derives L? So this is a proof sketch. A derives G in degree L. What does that mean? It means that G has this representation, right? And the point is that this has formal degree at most L. Right? And now, we are saying that mu satisfies. Wait, let's make sure that I got it right. I think I got it right. Okay. So mu satisfies, degree at degree L, the constraint system A. What does that mean? It means that, all polynomials. Wait, 1 second. Maybe I'm deriving a weaker conclusion. Okay, so what does mu? So I guess it's some algebra question that I'm now stuck on. So what does mu derives A in degree L mean? Means that for all. So I just want to check if this expression is going to be rendered non-negative or not. That's basically all there is to check. So I think it's just trivially true. So if this expression has degree at most L, then in fact it's a constraint that's enforced in my definition of satisfying a constraint. Okay, good. I think it's fine. And so each of these terms is actually going to be non-negative, and by linearity I would actually give G a non-negative value. And so this is not true. So So this L is somehow, you know,
Do we want 0, not L?
say it again.
Mu models A at 0, not L. Right? We want the strongest possible thing, right? Or am I missing something?
Mu models A at 0. Why would, oh, I see. If that's true, then in fact, here it might be degree. Yeah. Okay. So, okay. So that's a different statement than what I was going for, but I'll write that too, just because this is somewhat confusing. So suppose A derives G bigger than or equal to degree L. Suppose mu is, mu is a degree D pseudo distribution that, you know, satisfies A at degree 0. Okay, this means that L is useless. This is basically the usual definition. This is the natural definition you would have come up with. Then if L is less than or equal to D, okay, and in fact, you know, let me just, you know, because even I'm getting confused in the correct directions here. This might be the corollary to keep in mind. Just 1 second, Tim. So you understand? So you see, like, why? So let's do the proof of this corollary because it's definitely simpler and not confusing. So you know, what does A derives G bigger than or equal to 0 mean? It means that, you know, G has a representation like this. And, you know, this has total degree at most L. Now we are saying, you know, mu is a degree D pseudo distribution. What is that? And, you know, it satisfies, you know, A at this parameter L set to value 0. What does that mean? It means that, you know, for all H and S such that H times product I in S, Fi has degree at most D, the pseudo distribution renders such a polynomial non-negative. That's what our definition implies. And so now you see we are done because, you know, I can just apply pseudo distribution on both sides, and by linearity apply it term by term, and then each term is non-negative. So I'm done. So hopefully this corollary is clear. The one above, I think is true, but I guess I confused myself. So let's just focus on this corollary because in some sense, mostly that's what we'll need at least today. Good. Tim, you had a question?
Oh yeah, I was gonna say the corollary above. If S is non-empty, then I think the degree constraint won't be
Say it again.
satisfied.
Say that again.
So if S is non-empty,
Okay.
then the degree H plus the sum of max won't be satisfied. That won't be less than D. Because here your degree is also L, right?
Okay. I mean, this is only weaker, no? If the total degree is L, then certainly, you know, so if the total degree is, if the total degree of this monomial is L, then it certainly implies that degree of PS plus max degree Fi, comma L. I see.
Yeah, this is
I
backwards.
think might not have a pseudo distribution.
I see. It's backwards.
Value.
Certainly backwards. Wait, so what should I write here? What's the right way to fix this corollary?
I think the second corollary is true, but the first is not.
Yeah, the second is definitely true, and I want to write a good version of one, but I think
I think the degree of the pseudo distribution must be much larger.
Yeah.
Right. Yeah.
It must be like,
what should it be like?
Like L times M maybe.
No, that's not a reasonable thing.
Because like your S, the set S can be the entire set.
Sure. Yeah. No. I mean, Yeah, we want some reasonable definition. So so
L
it just
square
means that
we
I
might
screwed up. What?
like L square, because you might have at most L polynomials FIs.
L square. Actually, you know what? Let's just table this, okay? So it's good that we don't try to come up with a version online, because I'll screw up again. So that's my homework for today. I'll fix the statement here, and I think I convinced myself before the lecture that this was okay, but now I'm actually confused. So let's ignore this. Let's ignore the stronger corollary and just focus on the weaker corollary, okay? And in some sense, that does the job, because more or less that's what we're going to use. Sometimes generality is your enemy. Good. Very good. So hopefully, you get a sense of why we should define satisfying constraint this way. It, somehow tells us that whatever polynomials have certificates of non-negativity, in some sense, this corollary is the reason why we are defining satisfying constraints in the way we did. We're saying that, so in verse, whatever polynomials can be proven non-negative in low degree get non-negative pseudo expectations. Whenever mu satisfies A. So the intuition is that if mu satisfies, like in some sense, if mu was an actual distribution that was supported on the solution set of A, then whatever polynomial is non-negative on the solution set would have a non-negative non-negative expectation. We basically toned down that conclusion for pseudo distribution. We said, whatever polynomials we can prove non-negative in low degree will get, non-negative pseudo expectations. This is our goal. And we defined what it means for mu to satisfy the constraints in A in order to make this goal happen. Okay. So in some sense, what we're saying is, not all polynomials which are non-negative over A will get non-negative pseudo expectations, but whatever polynomials have a sum of squares proof of low degree of being non-negative over A will get non-negative pseudo expectations. We defined the concept of satisfying constraints to make this happen. Good. Is there any question about this? At least this idea should be clear, why we are defining satisfying constraints in the way we did. Feel free to stop me and ask questions, because we are coming to an end of our theory building exercise in like a bit. Good. So, two last things, so remember, we showed that whenever there was no sum of square certificate, there was a pseudo distribution. This was a duality statement, we wrote down, for the hypercube. There is an analogous duality statement, but it actually gets kind of complicated in the most general form. So I'm going to state it in a form that's useful to us, general enough, but not the most general possible. Okay. So here is again, I'm not going to prove this. Just state. So let's say, A is the system of polynomial inequalities as we've been working with so far. And we are going to assume in addition that this particular inequality is included in A. Okay. In fact, such sets are kind of important, and they occur lots and lots of times in applications. So in fact, make a definition for them. We call such sets explicitly bounded. Okay. So notice that hypercube has such a property. We can, without loss of generality, add the constraint that sum xi square in fact equals n, and it doesn't change the set. So, the hypercube, in fact, without loss of generality, has such a constraint in it. The other setting that we will consider a whole lot is, inequality systems over the unit sphere, over the real. So, that would constitute, inequality constraints like this, equality constraint like this, like, because we'll deal with like points on the sphere, and that also another example. But in general, the sets we deal with are going to be explicitly bounded. This in particular means that, the set of points we're looking at is always within some, ball ball of radius square root m around 0, right? That's what it means. But it means something stronger than that. It means that, this inequality is explicitly included in A. Okay, like the difference is that, it could be that in real life, A, like whenever A holds, it somehow implies that, some xi square is at most m. But, we don't want to reason about the degree of the SOS proofs for such an implication. So we just, ask that this inequality should be explicitly included in A. Okay, so we're going to work with explicitly bounded semi-algebraic sets. Then for all integers d, for all f polynomials of degree at most d, exactly one of the following holds. So for all epsilon bigger than 0, there exists a sum of squares proof of degree d. Well, again, I should use notation. For all epsilon bigger than 0, A derives in degree d the inequality f bigger than minus epsilon, or there exists a pseudo distribution mu of degree d. Mu satisfies A at degree d. Actually, you know what? Let's just use the weaker definition. So what is this saying? This is saying that, either A derives the inequality constraint that f is bigger than minus epsilon. So think of this as a proxy for f bigger than equal to 0. And, there's some issue that there's an issue with like closed and non-closed sets here, which is basically, forcing us to write it this way. So let's ignore that and think of this as a proxy for saying that, A derives f is non-negative. Okay. Then this is saying that either there is a degree d sum of squares proof that, f is non-negative starting from A, or there is a pseudo distribution which gives, negative pseudo expectation to f, and mu satisfies A. Okay, this is in some sense the duality theorem you should expect, saying that, either. So in some sense, what would be the duality? This is the analog of the statement that's saying that, either, there is an x, either, for all x that satisfy, so let's maybe say this, the analog for distributions, just to make sure it's clear what's going on. Either for all x that satisfy A, fx is bigger than equal to 0, or there exists a distribution. And what should a distribution be supported on? Well, there is at least one point where, if this does not hold, then there is at least one point where, in fact, f must be negative. So you will take a distribution which is supported on points where f is negative, but, satisfy A. So mu on x satisfying A, such that, expectation with respect to mu is negative. And so this is a statement which I'm sure you believe rather easily. And what we have is an analog for pseudo distributions. Here we are saying that, either a non-negativity can be derived in degree d. If not, in fact, there is a pseudo distribution that satisfies A, but in fact gives a negative pseudo expectation to f. Okay. Good. Very good. Okay. So let's do the final. Again, not gonna prove, but the final thing we want to do is like understand when can we compute these objects. Okay. So I want to write, in fact, the theorem statement only for computing pseudo distributions, because that's what we're going to use now. So here is a theorem. D is an integer, A is a polynomial system. Now, because we're talking about algorithms, we're going to think of the coefficients as rational numbers, okay? And then we are going to count the size of the input as, the sum of the bit complexities of the polynomials appearing in the input. Okay, very good. In the normal monomial representation, just like we did earlier, over Rn. And in addition, so remember we needed like this explicitly bounded condition to to write the duality statement. So we are going to need it here too. So we're going to assume that A is explicitly bounded. Then there is a n to the O of D. So n is the size of input. So this includes bit complexity. N to the O of D time algorithm to output a pseudo distribution mu such that mu satisfies A up to an additive error of 2 to the minus n. Okay, so let's again, make sure we understand this statement. What is this saying? This is saying that, I'm given a system of inequality constraints A, and I'm assuming that it's explicitly bounded. So, it has some constraint, some xi squared less than equal to m for some number m that appears explicitly in it. And then, I count the bit complexity of the representation of all polynomials. And let's say that bit complexity is capital N. Okay. That's the size of the input. Then there is an n to the O of D time algorithm to compute a degree D pseudo distribution. Okay. That satisfies the constraint system A. Okay. And the only thing I need to justify is like, or at least explain, is what is this up to an additive error of 2 to the minus n. So the point is that I cannot actually use algorithms to compute pseudo distribution that exactly satisfy constraints. And the more fine-grained way to write this would have been to just like write down the running time for every possible accuracy epsilon, but it's easier and easier in terms of notation, and also in terms of usefulness, to just like let some fixed small error bound of 2 to the minus n. And now I have to just like explain to you what does it mean to satisfy constraints up to an additive error of 2 to the minus n. It basically means that, for all, let's say, monomials, x to the alpha, actually, for all, SOS polynomials. So my constraints were for all SOS polynomials H. These were my constraints, right? And so what the pseudo distribution I'll find will not actually satisfy this. It will satisfy 2 to the minus n times, some sum of, let's say, L1 norms of coefficients of the polynomials. Again, I can afford to be loose about it because this 2 to the minus n in general, is designed to. So actually, I want to make this 2 to the minus capital N. And then, I'm actually okay in being cavalier about, the sum of L1 norms, etc., because, they're all going to be polynomial in N. So, in general, I'm going to be happy. Okay. But the important point is that, I can't quite get these inequalities to be satisfied exactly. I can't. Oh. So, it's minus 2 to the minus n. So it's like a small negative number. So I cannot satisfy this inequality constraints exactly. I'm going to lose a little bit on them. But, we'll have to somehow argue and make sure that whenever we use them in algorithms, this small error somehow doesn't bother us. Okay. Good. So, okay. So I had some more general theory, which was somehow going to be essential for next lectures, but I'll actually do them in those lectures because I think I have already put many of you to sleep. So it's time to wake up and do, some CSPs and some more optimization problems again. So what we'll do now is take a break, 10 minutes. So we'll resume at 5:47, roughly, and then come back and, formulate, constrained optimization problems and look at some basic problems like maximum independent set and prove lower bounds from them, starting with what we did the last time. Okay, good. So see you back at 5:47. So let's begin again. Yeah, so let me, start with the problem, which is kind of like the problem we saw last time, but like slightly different. Okay. So remember, we dealt with the 3 XOR and more generally K XOR problem the last time. And how did we write an instance down? We'll say, okay, an instance consists of, collection C1 through CM, which are basically just subsets of triples of variables. So they are just triplets of variables. For each of these CIs, I also had some right-hand sides, B1 up to BM. And basically they defined a constraint, they defined, a 3 XOR system, which basically said XCI equals BI, or equivalently, BI times XCI is 1, right? And so the satisfiability version of the 3 XOR problem was simply, the question of finding an X. So the satisfiability version is simply, does there exist an X such that, BI XCI equals 1 for all, M of the constraints, right? That was the 3 XOR problem that we saw the last time. Let's actually, we actually considered the max 3 XOR problem. Or at least we started talking about the max 3 XOR problem, where we defined like this polynomial I, which was like half plus 1 over m sum I bi xci. We call this part I, and we said, okay, let's look at like this val I polynomial. I guess maybe 1 over 2m, whatever. And, we looked at the problem of, approximating val I or proving good upper bounds on val I, right? Good. So instead of looking at the max 3 XOR problem though, let's look at the satisfiability version for a second, okay? Let's continue to look at it anyway. Good. So what did we do last time? We, for both of these related questions, we asked for, so last time we asked for a certificate of non-negativity for, polynomials 1 minus epsilon minus val I, which is actually equivalent to, up to some constants to giving a certificate for, let's say this polynomial. So we said, okay, for some non-zero epsilon bigger than 0, is there a SoS certificate of non-negativity, for this polynomial? And the reason it was interesting was because the true value for the random instance that we actually did define. So remember the CIs, were randomly chosen last time. The BIs were also randomly chosen, and for each I, the choices were independent. And then we proved that, with like, let's say 99% probability, the true maximum of, this polynomial is in fact, sorry, I guess I need to write val I here to make sense. But, we saw that the true maximum of val I is in fact just close to half. It's supposed to be half plus little of 1, right? That's what we proved. In fact, like if you take n over epsilon square constraints, then in fact we proved, by some union bound argument that this is at most half plus epsilon with like 99% probability. So this polynomial is certainly non-negative over the hypercube, because for some tiny enough epsilon, 1 minus epsilon will exceed half plus epsilon. But, we were hunting for certificates of non-negativity, low degree certificates of non-negativity in principle. And we basically proved that there is no such certificate for even like omega n degrees, right? Even though there is always a certificate of degree 2n, we proved that, for some tiny enough constant n, there is no certificate of degree cn, right? That's what we proved. Today, let's ask the following potentially harder question. And this is, by the way, like going back to the difference between questions 1 and 2, okay? So today we define 2 questions. Given a system of polynomial inequality constraints, check if a certain polynomial is non-negative over a solution set for it. That's basically how you can think of this question, the question we studied the last time. Look at this particular polynomial and decide if it is non-negative over the hypercube, right? But today we studied that, we can formally create a harder or like a stricter formulation by just like throwing all the constraints into our system A and asking for feasibility of it. Okay. So let's phrase the formulation number 2 that we studied today, okay, for the 3 XOR problem. So now, our system A is simply xi square equals 1 for all I. That's definitely there. We are still looking over solutions, over the hypercube. But then I also have this system of constraints, bi xci equals 1 for I from 1 through m. So I'm looking, so now I'm like literally phrasing the satisfiability question. Okay. I'm asking, is there an X over the hypercube? So over the hypercube part is like encoded here, right? That satisfies each of the 3 XOR constraints that appear in my instance. So notice that for random instance that we studied the last time with, m bigger than, let's say, n over epsilon square, with like probability at least bigger than, let's say, 0.99, A is, empty. There is clearly no X, right? The instance is, in fact, not just unsatisfiable, it is highly unsatisfiable. In fact, no more than half its epsilon constraints can be satisfied. And so certainly A is empty, right? But we can ask, if A is empty, right? Then we know. So we already know that if A, either A is empty, either A is non-empty, or there is a derivation from A of the bogus inequality -1 bigger than or equal to 0, right? So in particular, Krivine and Stengel told us for some large enough L, A derives -1 bigger than or equal to 0 because A is in fact non-empty. A is in fact empty, right? Now, of course, for proving this statement, you don't need Krivine and Stengel. You can actually give a very standalone proof on the hypercube for this fact, like L equals 2n in fact would work. But as a special case of this deep theorem that we stated today, Krivine and Stengel also promise us that there is such a refutation, and we can ask, is there a low degree refutation? Can I choose L, significantly tinier than n, and still ensure that A can be refuted? So the question I can ask is there a low degree refutation of the system A? And so in fact, I want to prove that this problem is hard even in the satisfiability refutation version. So even the stricter formulation that we studied today. So 2 is a strictly, like the second formulation, the second problem we studied is strictly stronger than 1, in the sense that whenever you can somehow provide a solution for 2, it also provides a solution for 1. I want to somehow show that in fact the stricter formulation also does not help us. Okay. And in fact, I'm just going to observe that what we proved the last time also gives, a negative answer for the second formulation. So I'm not going to do anything great and new. But let's, make the following observation for that. Okay. Again, this is a consequence of the theorems we already wrote down. But for this particular case, I'll just observe that they're easy to prove, directly. So let's let's make this observation. Suppose there exists a pseudo distribution mu of degree bigger than some Cn for some constant C that satisfies A. Okay. Then let's call this number D. Then A cannot derive in degree D -1 bigger than or equal to 0. So here's something that I think is actually trivial to prove, but I want to make sure that you understand this. I'm saying that I'm going to use this general duality we wrote down today to observe that in order to prove that there is no refutation, I can just exhibit a pseudo distribution, and the proof of this is very simple. Why is this true? Well, suppose there is such a pseudo distribution, and suppose in fact it happens to be true that there is also a derivation like this. Okay. Well, in that case, what would happen is, because there is a degree D derivation, and because mu satisfies, so we ignored this stricter definition, so I'm just going to write it like this. So suppose mu is a degree D pseudo distribution that satisfies A, then we know that in fact mu should satisfy every inequality that can be derived from A in degree D, right? So it would imply that the pseudo expectation of -1 would be bigger than the pseudo expectation of 0, which is 0. And of course, this is not true because we know that pseudo expectation of -1 is minus the pseudo expectation of 1, which equals -1, and which is not bigger than or equal to 0 by a simple observation. Okay, so what this means is that, in order to prove that there is no degree D refutation of the system A, it is enough to exhibit a degree D pseudo distribution that satisfies the constraints in A. So what this observation says that if you want to prove the absence of a low degree refutation, exhibit a pseudo distribution. Okay. So last time we constructed a pseudo distribution. Okay. But the only fact we proved about it in class. So last time, what did we do? We constructed a pseudo distribution on the hypercube that satisfies val I is 1, right? You remember we proved this? We proved that in fact, mu of degree D, which is like omega n, that satisfies the pseudo expectation of this val I polynomial that just counts the fraction of 3x or constraint satisfied by x is in fact equal to 1. That's what we proved, right? I want to observe in fact that that we not only proved this, the same pseudo distribution in fact also satisfies A as constraints. So why is this true? Oh, can someone unmute themselves and tell me why should this be true? Okay, I mean, I didn't expect because like this, it's almost like a long answer type question that I'm asking you to answer. So let's let's do it in like maybe a couple steps. Okay, so why is this supposed to be true? So what does it mean? So let's understand, what does it mean for mu to satisfy the constraint system A, right? So for equality constraints, so let's recall this, so because we're doing it the first time, let's make sure that we understand the definitions correctly. So what does mu satisfying A mean? Means, that for all polynomials, so remember A for us is just, equality constraints, which make the life notationally easier. Okay, so they're all equality constraints for us, right? So what does it mean that mu satisfies A? It means that for all polynomials H, the degree of the polynomials should be, so we are looking at 3 XOR constraints. So each of our constraint polynomials is degree at most 3. So for all H of degree at most, let's say D minus 3, it should hold that, the pseudo expectation H times BI XCI minus 1 should be 0. Do you all agree that this is just, this is the definition we made at the beginning of the class today, just, specialized to this equality case? And this is literally what it means, right? Like for all H, which, so this degree bound is simply saying that, the degree of this polynomial that I'm taking the pseudo expectation of is at most D, right? And so we didn't quite prove this the last time, but in fact, our construction satisfies the stronger property that in fact, for all polynomials H times BI times XCI minus 1 is in fact 0. Okay, why is this true? Let's quickly verify that. Let's verify this. So first of all, by linearity, it is enough to verify for monomials. Okay, because for every polynomial h, I can write down as a linear combination of monomials, and then just like term by term prove the equality. Okay, so it's enough to prove for monomials h equals xs. Okay, for s of degree at most d minus 3. Okay, and s can be in some sense the hardest case of s is multilinear, but you can think of s as a multiset here, because we are allowing a higher degree even though it does not matter, it's like we are allowing s to have repeated indices today. So why is this going to be true? So let's look at multilinear case, because the other case is really in some sense even more the other case is in fact reducible to this case. So if if s is actual set, not a multiset, then we want to understand what is this pseudo expectation like. Like that's what we want to understand. And in fact, this is 0 if and only if the pseudo expectation of xs times xci times bi equals the pseudo expectation of x sub s. I just like opened it up, applied linearity, and remember that bi's are constants. So let's see why this has to hold true. And the thing has to it has to do with simply this observation that we made about this the set of all derivations. Remember what Grigoriev construction was? It constructed this degree d derivations, and then whatever constraints we derived in derivations, we set the pseudo expectation values to whatever appeared in the derivations. Every other monomial was set to 0, right? So notice that s is of degree at most, s is of size at most d minus 3. Ci is a set of size at most 3. So this monomial here is a degree at most d monomial. Good? Makes sense? Very good. Now, suppose suppose that first suppose the pseudo expectation of xs is 0. Okay, so what does it mean? It means that in the derivation process we did the last time, the pseudo expectation of xs was never set. So xs was never derived. That's what it means, right? Then I claim that in fact this is also 0. And this is a one-liner, so please unmute yourself and tell me why. This is mostly like a question of whether you recall the proof the last time. So I'm saying that if
Because
xs was, say it again, yeah. Sorry, yes, go on.
this is not derived also.
Exactly. So for a contradiction, so when will this not happen? When this doesn't happen if xs xci was derived, but xs was not derived. Well, but that's a contradiction. Why? Because if xs xci, so xs times xci, let's say, is in the derivations, xci is certainly in the derivation, because it's a constraint in our 3 XOR input formula, and the XOR of xci and xs times xci is of size at most d, because in fact it's a set of size exactly d minus at most d minus 3. So if these two are in the derivation, then by our rule for constructing derivations, xs should have been in the derivations, right? But it was not, because its value is set to 0. It means that xs times xci is also not in the derivation, and then we in fact set it to 0. Okay, good. So now so that's easy. So now suppose pseudo expectation of xs is not 0. Now what happens? Well, in that case, we proved that, so if I have two xs xci are both non-zero, then in fact we proved that this must equal the product of their expectations, because that's how our procedure derives them. Remember this? Good. Now what happens? Now we are done because what should this be? Well, xci equals bi is a constraint. So pseudo expectation of xci must be bi, right? So we have proven that this monomial has value bi times pseudo expectation x sub s. And now we are basically done because, we have proven that this is equal to bi times, pseudo expectation of xs, and bi square is 1. So we are done. Okay, good. So what have we proven? We have proven that in fact, the construction we did the last time, in fact, satisfies, this potentially stricter formulation. So in fact, it not only gives pseudo expectation val I equals 1. In fact, it satisfies the 3 XOR constraints as formal constraints in the system A. Okay. Actually, this should not have been. I mean, we did things in reverse. Last time we pulled out this derivation D set. Just is almost in an ad hoc way, right? But now, in fact, you can go back and look at what this der D set in fact is. Der D set is literally all the constraints, all the constraints that can be derived in degree D from the system A. So the system that we like, the derivation procedure that we define, in fact, is same as write down all the. So I'll make this a formal statement. So, um, so the del D system that in fact we constructed the last time is same as all constraints that can be derived from the system A in degree, in sum of squares, like, all constraints can be derived via sum of squares proof of degree at most D from A. And so in some sense, our procedure itself was construct all possible, polynomials, construct all possible, polynomials whose expectations are rendered non-zero by means of degree at most D proof starting from the constraints, and give them the values that you derived, set everything else to 0. So it's not a surprise that we ended up satisfying all constraints, because we literally defined mu in the way that it satisfies all the that it would satisfy all the constraints. And so good. So in particular, we discovered that even if you were to write this second formulation, which is formally stronger to construct refutations for 3 XOR, it would not really help you. The lower bound we constructed the last time, in fact, applies to even this stricter formulation. Very good. So what do I want to do next? I want to now. So the problem that we just studied, in fact, has a good name. The problem that we just studied is called refuting random 3 XOR. And in fact, we just proved that, sum of squares, of degree some omega n cannot actually refute, random 3 XOR constraints. In particular, it cannot prove that, there is no solution that satisfies all the constraints. That's what we just established. What I want to do is, spend maybe, at most, let's say 15 minutes, discussing this problem in somewhat more generality, and just tell you, why we might care about it. And then, we'll go back and, sketch the idea of reductions. Okay. Good. So first, I want to, we defined CSPs long time ago, and in particular, I should say, I would still prefer if you could all keep your videos on, if possible. Again, not required. Good. Yeah. So, so I defined, constraint satisfaction problems earlier. 3 XOR was an example of it, but I just want to recall, this definition. So remember, if I have a CSP with predicate P, so P is, just some k-bit Boolean function. So, it takes values, in some k-bit vectors and outputs 0 or 1. You can think of this as, satisfied, and this as like unsatisfied constraint. So that's basically the interpretation of 0, 1. You could call it like false and true if you like. And then, each instance of CSPP can be described, just like we did for 3XOR, by a bipartite graph where we have constraint vertices on the left and, variables on the right. Okay. And now in 3XOR, what I would do is just connect the constraints to the variables that appear in it. But, in general, the Boolean function, like 3XOR doesn't care about order of bits. Like it's the same function, whether or not, whether you like think of, like in some sense, it does not, it's for 3XOR, it's not important which one is the first bit and which one is the second bit and which one is the third bit. In general, though, there can be functions which care about, the order, right? And so in order to somehow have that in mind, I will use this slightly more cumbersome notation to define CSPs for you now. So let's say, let's say P is a K, so P is a K bit predicate. So each CI would have, K connections. Okay. And, in fact, these edges are labeled. So, so in some sense, I can think of the first edge from C1 and second edge from C1 and third edge from C1 and so on. And in some sense, the first edge is supposed to denote which is the first variable, and second edge is supposed to denote which is the second variable, and so on. Okay. So these edges can be thought of as labeled by like pairs, ij, and ij stands for jth variable in ith constraint. Good. And now, in general, I'll give an example very soon, but we will have a certain literal pattern. So, for each C sub I, I'll have a bit vector. So this is basically my way to, allow negations of, variables that appear in the constraints. I'll explain what that means in a second. But this is basically a complete description of a CSP instance. So, the CSP instance is specified by this bipartite graph with labeled edges and, literal patterns Li or L1, L2, L sub m, one for each constraint. Each of them lives in plus minus 1 to the k. Good. So now what does it mean? So just to make sure that this notation doesn't confuse, let's take the example of the 3-sat problem. If you remember what the 3-sat problem is, the constraints look like let's say x1 or not x2 or x3. And so basically for describing this constraint, what I will do is I'll say, let's say this is the first constraint, and I'll say C1 is the first edge is to variable 1, the second edge is to variable 2, the third edge is to variable 3. And now, only, so, now I have to describe what this L sub I is. L sub I basically just, tells you which variables are negated. So wherever it's like, let's say -1, I'm going to think of that variable as negated. And so, L1 of 1 will be 1, L1 of 2 would be -1, and L1 of 3 would be 1. This just says that, the second variable was negated. Okay. So a instance is specified by, telling you what are the variables that appear in each constraint and which one of them are negated. Okay. Very good. Now, in general, so this was for 3-sat. In general, the goal in CSP with predicate P is to, so this is the max CSP goal, maximize P of Ci of Li dot Y. So what this means is, take the variables, take the k tuple of variables, the ordered k tuple of variables that appear in C sub I. Okay. Now you're trying to evaluate, what happens to an assignment Y to it. So you wanted to evaluate what happens to Y, just like take the projection of Y to the variables that appear in CI, negate them according to the literal pattern L sub I, and see if on this k tuple that you've derived from Y, if the predicate P is satisfied. this is just like a cumbersome way to, describe what it means for an assignment to satisfy a 3-set constraint, which might have, negations. Okay, so hopefully this is not too daunting, the notation itself, but that's how, you would write it. Good. And, so this is the max CSP goal. So, maximize this overall, y n plus minus 1 to the n. But you could also look at, the satisfiability goal, the kind of stuff that we did today, which is, is there an x that satisfies, p of ci, li, y equals 1? Or is there, for all of the m constraints? Good. So, in order to prove a lower bound for max 3XOR, we actually constructed a random instance. And just like we saw today, we proved, in fact, a lower bound for refuting, like proving unsatisfiability of the instance, right? So we, in fact, proved something stronger. We not just like ended up proving a lower bound or an integrality gap for max 3XOR. We, in fact, proved that, if you wanted to use sum of squares to refute the system of CSP constraints, for 3XOR, then, in fact, you require degree omega n, okay? We'll now, phrase this goal, this average case goal, in a standalone way, because actually it turns out that this itself is an interesting problem. Even though, for us, it was just a vehicle to prove integrality gap right now. By itself, this is an interesting problem. So I want to define it separately. Let's say, it's specified by some predicate P. Okay, so P could be SAT, P could be XOR. XOR is what we saw today, but P could be any other predicate in general. Okay, so the input, so in here, in some sense, the goal, so let's say informally, the goal is to prove or certify right, to prove unsatisfiability of a system of, constraints that come from a random CSP. Okay, that's the goal. So what I will do, so in fact, you already know that, what is a random CSP P instance? Choose, the CIs at random and independently. So these are like, going to be just k tuples of variables. Choose them, uniformly and independently from n to the k. For each CI, choose the literal pattern also at random and independent. Okay, so that's what I mean by a random CSP. Okay, just like construct m constraints by picking the k tuples that appear in each constraint at random, and then the literal patterns on those constraints also at random. Okay. Now, just like we proved the last time. So here is a proposition that follows from the same union bound like argument that we did the last time. If m is bigger than some O of n over epsilon square, then opt I for the CSPP is at most. Now, what should the value be? For 3XOR, remember, a random assignment satisfies about half the constraints. And then, we proved that, by union bound argument, we proved that, in fact, no assignment satisfies more than, like, sufficiently more than half fraction of the constraints, right? So the analog for arbitrary predicates P is, what you would imagine, whatever is the fraction of constraints satisfied by a random assignment plus epsilon. So what this P inverse 1, remember, is, the set of all assignments that satisfy P. And so P inverse 1 over 2 to the k is basically the fraction of assignments to P that satisfy, the predicate. And we are saying, that if I take large enough number of constraints, so this O actually depends on k, of course, but we are thinking of k as a constant for the purpose right now. Then, opt-I is, basically close to whatever is the value, whatever is the fraction of constraints that can be satisfied by uniformly random assignments in expectation. Good. So I've been a little bit fast. So let me take a 30-second pause and make sure that there are no questions, but mostly like definitional things are going on. So hopefully things are still clear. So the definition of a general CSP and a random CSP makes sense. And it also makes sense that a random assignment, or at least no assignment, satisfies significantly more than this P inverse 1, the size over 2 to the K fraction of the constraints. Good. So now I can state the refutation problem, which is the problem that we so the problem that we used, the problem that we discussed today for XOR was, to understand if, there is an assignment that satisfies all the constraints of an XOR system, right? I want to now, define that problem more generally for, a random CSP instance P, okay? But in fact, so let's maybe write it down. So today we asked for, SoS certificates of feasibility for the random 3 XOR CSP. Okay. Now, to be honest, we never defined the problem of constructing certificates of feasibility, in a way that does not relate to SoS, right? But of course, the problem itself can be defined without talking about sum of squares. So that's what I want to do now. Okay. Even though, of course, we are interested only in like constructing sum of squares certificates of, sum of squares refutations. Our goal is to really study the existence or non-existence of sum of squares refutations. I want to, define the problem of constructing refutations for CSP in slightly more generality. And then we'll come back to SOS refutations, of course. So here is a definition. So I'm talking about, what is a refutation algorithm in general, okay? And of course, you already know what the sum of squares refutation algorithm would be, but I'm trying to define this in more general, and I'll connect back to what you already know in a second, okay? So a refutation algorithm for random CSP with predicate P takes input an instance I, okay? And it's supposed to output a value, a number, U. U stands for upper bound. Okay, with the following guarantee. So, this algorithm is trying to construct an upper bound on, what's the fraction of constraints that any assignment can satisfy in a CSP instance. Okay. So the correctness is that it should always be a correct upper bound. And actually, this property should hold for every instance, not just a random instance. For every instance I of this random of CSPP, U should be bigger than the largest fraction of constraints that any assignment can satisfy. If this is all I wanted, if this is all I wanted, then in fact there is always a very simple refutation algorithm for all CSPs. And what is that algorithm?
Output 1.
Yeah, exactly. You can always output 1 and you can satisfy this requirement of correctness very easily. And so, I'm going to force you to do something interesting by asking that with probability at least 99% over the choice of the instance I from random CSPP distribution. So like the sampling process that we described earlier, it should hold that U is at most 1 minus delta for some delta bigger than 0. Okay. So basically, if delta is strictly bigger than 0, then the second condition says that, with probability at least 99%, you will output a value which is strictly smaller than 1. In particular, you will prove that instance, you will assert that the instance is unsatisfiable, that there is no way to satisfy all the constraints with a single assignment. Okay, good. So just so that you see why this is related to what we are doing, what's the refutation algorithm we analyzed for KXOR? So the refutation algorithm we analyzed it was simply, compute max over all pseudo distributions of, let's say, degree D of the pseudo expectation of the val I polynomial, right? And output this value. I guess I can just simply write this. Okay, so who wants to tell me? So this is the algorithm we've been analyzing, right? Like, and we proved guarantees on it for whatever, like various values for degree D, etc. Can someone tell me why this is a refutation algorithm in the sense of the definition here? Right, okay. So actually, let me rephrase my question. Why does this algorithm satisfy condition number 1?
Stabilization.
It's a relaxation. Yes, exactly. So in particular, so as Jeff is saying, this value is the value that output in this algorithm is always bigger than opti. Why is that true? Well, because I'm taking max over all pseudo distributions of degree D. All actual distributions, in fact, over the hypercube are pseudo distributions of degree D. In fact, they are pseudo distributions of degree infinity. So in particular of degree D. And if there is an assignment that satisfies opti fraction of the constraints, then in fact the maximum will definitely be larger than opti. Okay, so hopefully you see that the algorithm we were analyzing was this specific algorithm, and our algorithm naturally thinks about certificates, naturally thinks about constructing certificates of non-negativity, and in particular also like, okay, equivalently upper bounds on the val I polynomial. But in general, I could have asked this question for all algorithms, and that's what I did here. Like I phrased this question without referring to sum of square certificates. So this algorithm is a like this. Why does this algorithm serve as? Why does any algorithm that satisfies the requirement here serve as a certificate? Because of the guarantee 1, right? We know that whatever value it outputs is always bigger than equal to opti. So, if it outputs a value less than 1 minus delta, we are absolutely sure that the instance is unsatisfiable. Okay, so in particular, this algorithm itself, so maybe I'll write this down. Algorithm never incorrectly outputs unsatisfiable. And that's why, you could think of it as a certifying algorithm. Because whenever it says that the instance is unsatisfiable, it is right. Okay, very good. So why am I telling you about all of this? The reason is that the historical the history of this whole thing is kind of reversed. People didn't hunt for sum of square certificates of unsatisfiability, etc. for 3XOR at first. They actually tried to solve the refutation algorithm, the question of constructing efficient refutation algorithms at first. Okay. Okay. So this definition that we wrote down actually, was first, like this idea of studying refutation algorithms was studied first by Feiger. And he asked, if I look at, let's say, a random random 3XOR or whatever, is there an efficient refutation algorithm? And so when he was studying it, and in fact it's still true now. So let me assert the following fact. this is right for 3 XOR. So, we studied the question of, constructing refutations or like certificates of, upper bound and the value of a 3 XOR instance with M, which were basically N over epsilon square constraints, right? And what we realized is that at least if you're looking for sum of square certificates, then there is no such certificate unless you, used, degree, which is linear in N, right? And so that corresponds to running times, which are, exponential in N. And so certainly it does not give us a polynomial time refutation algorithm, at least if we were to use sum of squares, right? Well, not so. So the fact here is asserting something, in terms of what we know about all refutation algorithms, not just sum of squares. It's saying that that there is no known polynomial time. There's no known polynomial time refutation algorithm for, let's say, random 3 XOR when the number of constraints is, let's say, asymptotically smaller than n to the 1.5. Okay, so
what happened to Grant-Schmidt? Sorry, Gaussian elimination.
Good.
You mean suicide?
Yeah. Okay. What's a good way to do this? What's a good way to do this? Yeah. Okay. Yeah, you're right. Let's do it for 3 sat. Yeah. I skipped over one page of my notes and I realized that I was doing something important there. So, okay. So, it turns out that so we have not studied this problem random 3 sat yet, but it turns out that there is no known refutation algorithm that, solves the problem in terms of, satisfying these two conditions and running in polynomial time whenever the number of constraints in the random instance is much smaller than n to the 1.5. And it turns out that, well, at least, Feige in 2001, and, he was right because he is still, like there is no known. So in 2001, there was certainly no known algorithm. And so in fact, Feige conjectured, and actually this is, now actually it's a pretty famous conjecture. It's called the random 3 sat hypothesis. He conjectured, that for some C bigger than, let's say some 2 to the k, so he basically, took this observation that nobody knew of an algorithm that worked when m was, order n. And this is just the right constant that makes the instance's true value small. Certainly there cannot be a refutation algorithm if the instance is satisfiable. But, Feige was saying something interesting. He was saying that, even when C is much bigger than 2 to the k over epsilon square, so the instance is in reality unsatisfiable, there is no known polynomial time. There is no polynomial. He conjectured that there is no polynomial time algorithm that in fact, functions in this refutation way that we just defined. And what was his motivation? Well, he did lots of clever stuff with it. So this is in 2001 that he proposed this, a conjecture, and he basically derived consequences to. So in his original paper, he derived like lots of new hardness results from this assumption. So, this is a stronger assumption than 3 sat being hard or hard to approximate, right? Like we are now conjecturing that a random instance of 3 sat is hard in a certain sense, in the sense that, there is no efficient refutation algorithm for it. And so, at the time, there were several results that people were trying to prove in hardness of approximation, which, they couldn't do starting with random 3 sat, starting with like worst case 3 sat. And Feige figured out how to solve some of them if he made this stronger assumption. So his assumption still stands. In fact, we probably have like a lot more belief in the truth of this assumption now than maybe in 2001. And Feige only used it for hardness approximation. But, since then, this conjecture and variants of it for other CSPs the analogous conjectures for other CSPs are now, in some sense, extremely useful in proving hardness results in like several different areas. So, you can prove lower bounds in learning theory. So, there were some really cool results that appear about 5 years ago that use, these random 3-sat and random CSP hypothesis to prove hardness of learning problems. And so that happened about in 2013. Well, I guess 7 years ago. And there was a sequence of papers that proved lower bounds that people were hunting for like 20 years, and like they realized that if you make this RCSP assumptions, then you in fact get them very easily. Even at the beginning, when Feige proposed it, these assumptions were already like central to constructing many cryptographic objects. So there are some pseudo random generators, if you know what those are, that you can actually build by assuming these conjectures. Like they provide security guarantees for this constructions cryptography. And so these, so I guess there are many more, but I only want to maybe state these 2 points. The point I'm trying to make is that these conjectures are extremely important, and in that they yield lots of interesting consequences. And so in general, we are interested in and so in general, we are understanding in general we want to understand the truth of this, how we want to like collect evidence for these conjectures. And for better or for worse, the best algorithm we have got for these problems happens to be, the algorithm that we are studying in this whole class. And so, it turns out that the best known algorithms for this problem is indeed the sum of squares algorithm. In particular, here's a theorem. I actually forget, the reference for this, unfortunately, but no worries. If m is bigger than n to the 1.5, and in fact, this algorithm simply uses degree 4 sum of squares. And it turns out that in some sense, the best that we know, the best this is the best algorithm that we know. The best algorithm that we know that manages to prove an instance unsatisfiable for random 3-sat works only when the number of constraints that you have is at least n to the 1.5. And that happens to be degree 4 sum of squares. And below n to the 1.5, we know of no polynomial time algorithm. In fact, at m equals cn, so at m equals cn, we already proved for 3 XOR, we already proved that needs degree at least omega n for refutation. It turns out, and I guess it was my plan to do a proof of this, which is like really a 5-minute proof, but now I will not. It would appear as another problem on your homework. It turns out that this, in some sense, in like 2 lines, implies that R3-sat also needs degree omega n SOS for refutation. And so, now we have like these 2 regimes, right? Like the stuff that we already did implies that if you have only theta n constraints, like m equals cn constraints, then in fact all like at least the sum of squares algorithm needs degree omega n, and therefore time exponential in n, in order to refute or like prove unsatisfiability of this random CSP instance. On the other hand, I'm claiming but not proving. This would be yet another problem on your homework. But both of these problems are easy, so I'm not going to ask you super hard things. That at n to the 1.5 and larger number of constraints, you can construct small degree refutations, right? And at this point, you could ask several questions. So what happens in between? So like, let's say m is bigger than some constant times n, but smaller than n to the 1.5. You could also ask what happens when, predicate p is different. It turns out that we kind of understand the answer to such questions completely now, even though we will not actually cover them in the class. Even though we will only like stick to the one proof that we done in the class, the 3 XOR proof. We kind of understand the answer to the question for all CSPs, and actually all densities of CSPs. So we actually know a complete answer to this. So we know And so what I want to do in the last 5 minutes is describe this answer to you. But again, I want to take a 30-second break and see, if there are any questions before that I can answer. Any questions so far? Okay, so what I'm going to describe to you is like the answer. So we already know, or at least I already claimed, that if you want to have polynomial time refutation algorithms, at least using SOS, then you need n to the 1.5 or larger number of constraints. And it's some weird, funky number, n to the 1.5, for R3 XOR or R3 SAT. And at least for R3 XOR, we proved that if you have at least if you have only order n constraints, then in fact you need degree omega n, right? And so what I'm going to do is explain to you, or just like describe to you, this property of the predicate that governs what happens to sum of squares when you design refutation algorithms. So and this will also demystify where this n to the 1.5 comes from. So let delta be the following quantity. It's the max over all distributions mu. Actually, let me remind you what. So a distribution mu on plus minus 1 to the k is said to be pairwise uniform if the first two moments, so if the mean of x is 0, and if the covariance of x is identity. Okay, so in particular, every pair of distinct variables is uncorrelated under mu, and the mean of x is mean of mu is 0. Okay, that's what pairwise uniformity means. I'm sure you've seen this before. So now define the following quantity. So it's the max over all distributions which are pairwise uniform over 0 plus minus 1 to the k of p of x, the expectation of p of x. So take the expectation of the predicate p under all under all pairwise uniform distributions and see what's the max value you get. Okay. So the theorem is, if m is asymptotically smaller than n to the 1.5, then max over all mu, this time mu are pseudo distributions of degree some omega n. So let's maybe remind ourselves that this is CSP with predicate P and I is a random instance. Then the value, of this sum of squares algorithm, on this random CSP instance with predicate P is equal to delta 2 plus minus little of 1. And so, we basically, so what this theorem says is that, you have this simple property which depends only on the predicate, which is its like maximum expectation over all, pairwise uniform distributions. And it completely describes what happens to the maximum maximum pseudo expectation of this, fraction of constraint satisfiable by any assignment in, this instance I under any pseudo distribution of degree some Cn. Because in particular, it says why is this like statement interesting? So corollary, if there exists a distribution mu which is pairwise uniform and E mu px is 1, okay? So if there is a pairwise uniform distribution, such that the expected value of the predicate P is 1, which is equivalent to saying that mu is supported on satisfying assignments of P, then for M let's call this A sub I, which is, the system of constraints that a CSP, with predicate P gives you. So what this is saying is that, you have a complete understanding of when you could prove unsatisfiability or construct certificates of unsatisfiability of constant degree, for a random CSP, and it is determined completely by, this property, this quantity delta 2, which is just the maximum expectation of P under any pairwise uniform distribution. So in fact, there is a generalization of it, but I don't have time to describe this to you. I thought it's good to know this result because it turns out to be useful and you might find references to it at other places. I had the plans to do reductions, at least it's kind of easy to do once we set up all this constrained machinery, but we didn't get there, which means that there's going to be a Diderot post for you and then some homeworks to work out. Good, yeah. So let's call that the formal end of today's class, and then we can take questions as usual. So I guess maybe one observation I'll note is that if you look at 3 XOR, guess if you look at P equals the 3 XOR predicate, so it's a predicate which is satisfied, so let's see. So P x is 1 if and only if x1, x2, x3 is -1. That's a 3 XOR predicate. Then consider the uniform distribution. You can prove that this is pairwise uniform. Actually, it's kind of easy to prove. And in particular, it implies that delta 2 of this P is 1. And so, that's just verifying something that you already know, but it's observing that one way to black box obtain the result for 3 XOR that we proved by hand is to observe that the delta 2 value for the 3 XOR predicate is in fact 1. And the same is in fact true for 3 sat if you try it out. So same holds for 3 sat 2. In fact, the same distribution actually works. Good. Okay. Anyway, I'll stop there, and we can take questions.
Shouldn't the theorem say that it is for small degree pseudo distributions?
O of 1 degree. Yeah. O of 1 degree pseudo
But
distribution.
you said it's like, no, the above one. For omega and degree pseudo distributions, the max would be delta 2. But
Yeah.
shouldn't it be like little O of n?
O of n.
Oh, O, yeah.
Yes. So yeah, it's an abuse of the O notation. So it says that
Yeah, less than Cn for some constant.
Yeah, exactly. So so in fact, this statement, now that you remind me, it's actually incorrect. So let's just make it O of 1. Or actually, just to make it similar to what we proved, let's just look at this. So now this is a constant. Then I think it is true that okay, now I think at least it's a formally correct statement. We're saying that there is some constant C prime, such that if you take the maximum of this quantity over all pseudo distributions of degree at most C prime n, where C prime is some constant, tiny enough constant, then in fact, you will get a value which is roughly delta 2.
Yeah.
So why is this surprising? Like the surprising thing is that, we know that the true value is supposed to be, so when is this, okay, maybe I should point out. So, in general, the value of the random instance we observed is close to this quantity, right? And this is basically the expectation over the uniform distribution of P, right? On the other hand, delta 2 is the maximum over pairwise uniform distributions. So in general, and uniform distribution is, but in particular, pairwise uniform. So delta 2 in general is larger okay. If it's the same, then in fact, the statement is saying that you will, in fact, be able to prove the right value, in fact, to construct a refutation in polynomial time. But if delta 2 happens to be, significantly larger than, in fact, delta 2 happens to be 1, while, E mu P, in fact, always, E uniform P is always P inverse 1 of 2 to the K, then in fact, you have a gap, as in, sum of squares does something much worse than what the true value would be. Yes, yeah, hopefully I fixed the statement here now.
Okay, Professor, I have a question about the statement as well.
Yes.
Like, how do you see like the pairwise independent solution is the best lower bound you can get? I agree if it's a greater equal to there, but why is your equality? If delta 2 is not 1.
It's okay. So the reason it is exactly equal is because we can prove that the value we can construct a degree O of 1 certificate that the value is at most delta 2 plus little O of 1. So yes, you're right. Like we kind of only did a very special case of the lower bound. So for 3 XOR, we proved that the value is at least delta 2 minus little O of 1. In fact, we proved exactly equal to delta 2. But the converse is also true, and I did not state that.